And today I'm here with another quantum field theory exercise, and actually this one is not really that much of QFT but more of quantum statistical mechanics. So it is exercise 21.1. We're moving on onto StatMech, and it's define the density operator as this, and using the rule that thermal averages are given by the trace of density operator with the quantum operator, show that for a quantum harmonic oscillator with the Hamiltonian given as this, the thermal average is of the number of excitations n is given by this. So how do we do this? Well, let's go over to here. So first of all, we know that rho, which is a density operator in quantum statistical mechanics, is e to the power of minus beta h over z, where z is the partition function, which is defined as the trace of e to the power minus bh. And if you expand this in the what does the trace mean? It means you do a sum over some set of some sort of eigen basis. So some sort of basis for the Hilbert space. So one natural basis to choose is the energy basis, where you do this. Okay, rather let's write it as E of n minus beta h and E of n, and this would of course give us because the eigen energy states are eigen states are eigen vectors of the Hamiltonian operator. This will simply, and you can replace the Hamiltonian operator with the eigenvalue, so that gives us sum over E of n e to the power minus beta en. Okay, and because this is just a complex number, then we can bring it together, we can bring it outside, and then bra E of n and cat E of n normalize, so that actually just gives us, and you see we recover the classical partition function as the sum over all the energy states. So the quantum the quantum partition function isn't really that much different from the classical partition function, just that you do a trace, and you choose a trace over the energy eigenstate, then you recover the classical partition function. So that is what Z is. Yeah, so this is Z. Okay, and what is the density operator? Well, it's the exponential here, e to the power of minus beta h. Since it's exponential of an operator, it is defined by the Taylor series or the Maclaurin expansion. So it's 1 minus its identity operator minus beta h plus beta squared over 2 h squared plus so on. Okay, so in case you are wondering what's the exponential of this Hamiltonian, so let's go ahead and compute the trace. So the statistical average of A dagger A is equals to the trace of rho, which is E minus beta h, where h is equals to omega A dagger A with A dagger A, and this is divided by the partition function, which is the trace of e to the power minus beta omega A dagger A. And okay, so what does the denominator simply gives us a summation over n, and we can choose minus beta, so we know that this is A omega n plus half. So we know that all the energy for the quantum harmonic oscillator, all the energy eigenvalues are n plus half omega. As a factor of h bar, we set h bar equals to 1. So what's the numerator now? It is we choose what basis would be smart to choose to trace over. We choose the number basis. So it's just a number eigenstates, and we do this, A dagger A, A dagger A. So we do the sum. So what is the sum? This term over here is simply n, and because the number eigenbasis is eigenvector of this number operator. So we do this, n e to the power minus beta omega. A dagger A simply gives us n, and then this is n, and yes. Yeah. Oh, sorry, there isn't a factor of half over here, I believe. So it's just n. Yeah. Yes. So we do this. We sum over sum of e to the power minus beta omega n. Then over here, we know the n normalizes, so we can take this out. Okay. So what is the numerator over the denominator? It is simply the numerator seems a bit difficult to do this sum, where the n goes over all of the integers, so it goes from 0, 1 all the way to infinity. Yeah, but this is a bit challenging, so let's do something a bit smart. We then derivative with respect to beta omega, put a minus sign in front, and then we do this, and then we have e to the power minus beta omega n. Okay, so then we have the denominator, which is simply the we can really do the thing. So okay, let's leave it as its original form. Okay, so then the numerator, we pull out the partial derivative, and then we realize that it's actually just a log of n e to the power minus beta omega n. Yeah, so we do this, then we take the derivative. So what is this? It's just this. So what is this thing inside? It's simply a GP. So the common ratio is e to the power minus beta omega. Then the first term is simply 1. So ln of this thing, and we take the derivative. Ln of this thing minus ln of that thing, so it is partial derivative with respect to this. Ln of 1 minus then this is simply minus e to the power minus beta omega. We take the derivative of the numerator, which gives us beta omega. It doesn't give us beta omega, it gives us plus e to the power minus beta omega. And then we, as the last step, we just divide both sides divide the numerator and denominator by e to the minus beta omega, so we get e to the power plus beta omega minus 1. And we have arrived at the expectation, the thermal average of this thing, and this is our answer. And we see, in fact, that is the correct answer. So with that, I've come to the end of this video. Hope you like it. Leave a like and subscribe. Have a nice day. Bye.